In this lecture, we are going to discuss the concept of states, actions, and rewards more in depth. This lecture is about how we encode states and actions when we're programming. Talking about states, actions, and rewards theoretically is nice, but eventually we're going to have to put this into code. As a side note, since rewards are just numbers, this is trivial. There is no need to discuss how we represent numbers in code. Let's start with the state. As mentioned previously, the state can be discrete or continuous. In a game like tic-tac-toe, the states are discrete because they are just different configurations of the tic-tac-toe board. If we make a robot that has sensors like a camera, a microphone, a gyroscope, a proximity sensor, and so forth, those would all be continuous values. So you would end up with a vector of continuous values. In fact, this takes us back to regular supervised learning. If our targets are categorical, how do we represent them? In code, if there are k categories, we will use the integers 0 up to k minus 1. So we might say that dog equals 0, cat equals 1, mouse equals 2, and so forth. Obviously, it does not matter which category is assigned which number. And the reason we want to do this is because at some point, we're going to have to use these categories as array indices. And so similarly, if we have big S states, then we'll represent them in code using the integers 0 up to big S minus 1. For continuous values, it makes sense to store them in a vector. Although, if you have something like an image, then it will be a three-dimensional tensor. So, more generically, if you have continuous values, you can think of them as a tensor with one or more dimensions. Now that you know how to represent states and actions in code, it's time to talk about policies. When I first started learning about reinforcement learning, I found policies to be kind of an odd concept. Well, actually, I found all of reinforcement learning to be kind of odd and foreign, but you'll get used to it. The idea of a policy makes sense at a high level, but it becomes somewhat ambiguous when you start thinking about how to represent it mathematically or in code. The policy is what the agent uses to determine what action to perform given a state. It's important to keep in mind that the policy yields an action using only the current state. It doesn't use any combination of the current state and previous states, and it doesn't use any information about rewards. Technically, as I mentioned earlier, the state may be made up of multiple observations, and that may also include the reward, although that is unconventional. But strictly speaking, the policy will yield an action using only the current state. The simplest way to think about a policy is that it's a dictionary mapping or a function that returns an action given a state. Here is such a function. As you can see, the only input is a state S, and it returns an action A, where the state S was the key to the dictionary and the action A was the value. The real question is, how can we represent this mathematically? This is why it's useful to talk about how we encode states and actions first. So imagine again we are in grid world. Your agent now has a dictionary representing what action to perform given the state, as you can see here. So for example, if we're to the left of the goal state, then the appropriate action is to move right. And just to be clear, the left of the goal state is 0, 2. If we're at the initial state, then the appropriate action is to move up. And just to be clear, that is the state 2, 0. Now, from the initial state, moving right is just as valid, since we can still reach the goal from that point. You can see that, although I've encoded the states here explicitly as tuples, we could gain more efficiency by encoding them as integers corresponding to the tuples, and using those integers to index an array. As you may recall from your computer science studies, indexing arrays is faster than indexing dictionaries. Thinking about policies as dictionary mappings is somewhat limited. There are two reasons for this. First is that this won't work if you have an infinite state space. you would need an infinite-sized dictionary, which is not possible to have. Second is that it doesn't allow our agent to explore its environment. Think of training your agent like teaching a baby. At first, a baby knows nothing. It must try new things in order to figure out how the world works and build up its intuition. A reinforcement learning agent is the same way. If it has a fixed policy and it only does the same thing all the time, then it can't gain new experiences. Thus, it makes sense for policies to be stochastic. Stochastic is just a fancy word for random. In other words, a more general way to represent policies is to represent them as probabilities. Representing policies as probabilities actually solves both of the problems I posed above. Let's see how. First, it deals with this problem of randomness. The common way of dealing with this in reinforcement learning to allow the agent to explore is to give it a small chance of performing a random action. So here is a Python function that can accomplish this. We first generate a random number. If this number is less than some small number epsilon, let's say 0.1, then it will choose an action at random from the action space. Otherwise, we will grab an action from our fixed policy, dictionary mapping. This method is called epsilon greedy, and you'll learn later in this section why it's useful and what the relevance of exploration is. So what about continuous state spaces? In fact, seeing policies as probabilistic easily lends itself to continuous or infinite state spaces. Imagine your state is a vector S. Now imagine we have some policy parameters W. The shape of W is the dimensionality of the state space by the size of the action space. For now, we'll presume that the action space is still categorical. So what do we do when we want to output probabilities for a set of categories? In fact, this is just like classification. We can use the softmax function. So now our policy is the softmax of W dotted with the state S. As you can see, this allows us to introduce a little more notation. It's common in reinforcement learning to denote the policy with the symbol pi, not to be confused with the number pi. For any given state, we can calculate a probability distribution over the action space, pi of a given S. Then, to decide which action to perform in the environment, we can simply sample from this distribution. This allows us to explore if necessary, but we can still treat this policy deterministically if we want, simply by using the argmax. Also note that it's not necessary to use a linear model as we are doing here. We can in fact use any function approximator, such as a neural network. Now at this point, you may be wondering, how can an intelligent agent possibly know what to do using only the current state? This is the problem we described before. Just by looking at a still image of the road, how can I know what the correct action is? If you're more inclined to think inside a supervised learning paradigm, you may insist that there should be a target here, so that the agent learns to associate this state with this action. But in fact, it's quite possible for an agent to learn how to plan for the future using experience collected by playing multiple episodes. Even without an explicit target for a given state, the agent can still learn what action to perform such that it maximizes rewards in the future. This is what we will learn about in the coming lectures.